sklearnmetrics pairwise distances argminmin. Description: explain in detail. Inputs: X, a NumPy array or a sparse matrix representing the input data, where each row corresponds to a data point. Y, a NumPy array or a sparse matrix representing the reference data, where each row corresponds to a reference point. Argmin, a NumPy array containing the indices of the closest reference points for each input data point. Each element in argmin corresponds to the index of the closest reference point in Y for the corresponding input point in X. Min distances, a NumPy array containing the minimum distances between each input data point and its closest reference point. The ith element in min distances corresponds to the minimum distance between the ith input data point in X and its closest reference point in Y. Steps: calculate the pairwise distances between all input data points in X and all reference points in Y. Using a chosen distance metric, default is Euclidean distance. Find the indices of the closest reference points for each input data point based on the calculated distances. Determine the minimum distances between each input data point and its corresponding closest reference point. Metrics: the chosen distance metric, e.g., Euclidean distance, Manhattan distance, cosine distance, is used to determine the closest reference points. Visualization plots: scatter plot input data points can be visualized as points on a scatter plot, with different colors or symbols representing different clusters based on their closest reference points. Heatmap: the pairwise distances between all input data points and reference points can be visualized as a heat map to show the distance relationships between all data points. Metric: the distance metric used to calculate the pairwise distances. Common options include Euclidean distance, Manhattan distance, cosine distance. Axis: the axis along which the distances are calculated. Axis 1 calculates distances between each input data point and all reference points. Not directly applicable. Pairwise distances argmin focuses on determining closest points, not uncertainty measures. Challenge 1: computational complexity. Calculating pairwise distances between large datasets can be computationally intensive. Sample use case that resulted in Challenge 1: working with a dataset of 1 million input data points and 100,000 reference points. Fixes to Challenge 1: use efficient distance calculation algorithms, e.g., KD tree, ball tree. Consider using a sparse matrix representation for X and Y if there are many zeros in the data. Challenge 2: handling high-dimensional data in high-dimensional spaces. The concept of closeness can be less meaningful due to the curse of dimensionality. Sample use case that resulted in Challenge 2: working with image data, where each data point is represented as a high-dimensional vector. Fixes to Challenge 2: consider dimensionality reduction techniques, e.g., PCA, before calculating distances. Use distance metrics that are more suitable for high-dimensional data, e.g., cosine distance. Challenge 3: choosing the appropriate distance metric. Selecting a suitable distance metric depends on the nature of the data and the intended application. Sample use case that resulted in Challenge 3: working with text data, where the Euclidean distance might not be appropriate for capturing semantic similarity. Fixes to Challenge 3: explore different distance metrics relevant to the data type and task, e.g., word movers distance for text data. Consider using domain-specific knowledge to inform the choice of distance metric. Challenge 4: handling missing values. The function might not handle missing values appropriately, leading to incorrect distance calculations. Sample use case that resulted in challenge 4 working with a data set containing missing values in the input data or reference points. Fixes to challenge 4. Impute missing values using techniques like mean imputation or KNN imputation before calculating distances. Use distance metrics that are robust to missing values, e.g., Manhattan distance. Challenge 5 data scaling. The results can be sensitive to the scale of the input data, particularly for metrics like Euclidean distance. Sample use case that resulted in challenge 5 working with data sets where features have different scales. Fixes to challenge 5. Scale the input data using standardization or normalization before calculating distances. Consider using metrics that are less sensitive to scale, e.g., cosine distance.